Welcome to today's episode, where we dive into the mind-bending realities of physics as we approach the end of the universe. Whether you're a science buff or a curious mind, get ready to explore some of the most intriguing and perhaps perplexing theories that govern our universe's ultimate fate. If you're under the impression you know exactly how the universe will meet its end, think again. The truth is, no one can say for certain what twists and turns lie ahead. From scenarios like the Big Crunch to the Big Rip, from cycles of rebirth to eons of darkness, the possibilities are vast and varied. Yet, that doesn't mean predicting the universe's finale is outside the reach of science. By delving deeper into the cosmos as we know it today, we can begin to piece together clues about its eventual fate. I'm Alex McColgan, and this is Astrum. Today, we're embarking on an exploration into the distant future of the universe, a future devoid of planets, stars, galaxies, atoms, molecules, and even life itself, a future where the universe is on its deathbed. How much time remains until we reach this stark reality? And could there be an afterlife for the universe itself? These questions may seem daunting, yet the answers are intertwined with our grasp of a fundamental force: gravity. Gravity typically acts as a binding force, either slowing objects as they drift apart or accelerating them as they draw closer. This is why, prior to the discovery of dark energy, astronomers believed that gravity was gradually slowing our expanding universe. They even developed a parameter known as chi to quantify this deceleration. But as we'll see, the story took a turn with new scientific insights. As the 20th century drew to a close, groundbreaking observations of distant supernovae led to a startling revelation. The universe wasn't slowing down as expected, but rather it was picking up speed. This discovery shifted the entire paradigm of cosmic dynamics. The acceleration of the universe hinges on the type and distribution of matter and energy it contains. While the energy from ordinary matter produces a gravitational pull, something profoundly different must be driving the mysterious force that's pushing the universe to expand at an increasing rate. We've named this elusive force dark energy, but its true nature remains one of the greatest puzzles in modern cosmology. Despite our limited understanding of dark energy, it is crucial to predicting the ultimate destiny of the universe. Depending on its characteristics, dark energy could intensify the universe's expansion, stabilize it, or even cause it to reverse. Instead of exploring just one of these outcomes, we've created an extensive flowchart that maps out all potential fates of the universe, from the nature of dark energy to the eventual demise of everything we know. Most cosmologists believe that dark energy likely fits into one of two primary theories. The most widely accepted notion suggests that dark energy is the intrinsic energy of the vacuum of space itself. The primary alternative posits that dark energy might be the energy from new fields in the cosmos, fields that represent collections of yet undiscovered particles, potentially constituting a completely new type of matter. Imagine a universe filled with types of particles we've never seen before, far beyond electrons or quarks. This is the starting point of our exploration into dark energy theories, which take us through wildly divergent and potentially devastating scenarios. One critical aspect we must examine is vacuum energy. Is the vacuum of space stable, or could it shift to a lower energy state through a phenomenon known as quantum tunneling? The simplest outcome would be a stable vacuum, where dark energy remains constant, propelling the universe into an endless expansion, leading to what's called the Big Freeze. In this scenario, the universe grows exponentially larger and colder. Interestingly, here on Earth, or even across the Milky Way, life would seemingly go on unchanged because the mass concentrated in our galaxy is enough to offset the repulsive force of dark energy. However, if you were to look beyond our galactic neighborhood, you'd witness distant galaxies accelerating away at such speeds that they eventually vanish beyond an event horizon. Much like the boundary of a black hole, crossing this horizon means severing all ties with the cosmos we once knew. Beyond this point, there's no returning or even sending a signal back to what was once our cosmic home. One by one, We'll watch as galaxies outside our local group, where gravity binds us together, fade into the cosmos. Their light will stretch and redden, remnants from just before they slip past the event horizon. Over time, this glow will dim to whispers, eventually vanishing from sight. Billions of years from now, astronomers might gaze out into the void, unaware that the universe once teemed with galaxies beyond our own Milky Way. But what about the fate of the Milky Way itself? It's a tale of cosmic entropy, a more subdued demise dictated by the second law of thermodynamics, which states that systems evolve towards states of higher disorder. Every process, from stars burning hydrogen to helium, planets heating under their suns, winds sweeping across landscapes, and even the simple act of eating a carrot, all contribute to the inexorable rise in entropy. As the entropy in the Milky Way peaks, the stars will exhaust their nuclear fuel, planets will freeze over, winds will die down, and the cosmos will no longer sustain life as we know it. The remnants of matter will drift towards the inevitable collapse into black holes, which themselves will slowly evaporate into radiation. Eventually, what was once a bustling galaxy will reach a state of complete thermal equilibrium, a vast, cold uniformity where nothing happens, and time loses all meaning. The seemingly eternal fate of the Milky Way is ominously dubbed the heat death, not because it's sweltering, but rather the opposite. It's a universe without heat exchange, devoid of any temperature variations or energy transfers. Indeed, reaching this inert state might take unimaginably long. Yet, if dark energy is truly the result of a perfectly stable vacuum, then this fate of eternal stasis is inescapable. However, there is a speculative glimmer of hope at the end of this cosmic narrative, suggested by Sir Roger Penrose, a Nobel laureate and distinguished physicist. Penrose introduces an idea known as conformal cyclic cosmology, where he suggests that the end might just be another beginning. According to his theory, the radiation-saturated universe of the far future could become indistinguishable from the conditions of the Big Bang. Essentially, each epoch of infinite expansion could trigger a new Big Bang, kickstarting a fresh cycle of cosmic events. While evidence for this theory remains scant, it offers a captivating possibility that our universe's end could merely be a prelude to another beginning. If the prospect of a big freeze sends a chill down your spine, I have some news that might shift your perspective, both good and bad. The good news is that there's reason to believe the vacuum state that facilitates dark energy, potentially driving us toward the big freeze, might not be permanent. In fact, we might avoid the big freeze scenario entirely. This hope stems from recent research into the Higgs field, particularly measurements from CERN suggesting that the Higgs could settle into a lower energy vacuum state than our current one. To visualize this, imagine an apple falling from a tree, hitting our friend Isaac Newton on the head, then rolling into a slight dip in the ground. Not far off, there's a deeper hollow and even more stable resting place for the apple, if only it could overcome the intervening rise. In classical physics, the apple would remain trapped in its first dip, but in the quantum world, it's possible for the apple to tunnel through the barrier to this lower dip. Similarly, the Higgs field might quantum tunnel into this more stable state, potentially altering the fate of the universe. This theoretical possibility may not be immediate solace if we're heading toward a vast, cold void, but it offers a flicker of hope that the universe might reboot itself long after we're gone. And perhaps, just perhaps, that thought offers a bit of comfort. Similarly, the Higgs field has potential different states, akin to the varying depressions in the grass, each representing a different vacuum state. Yet another compelling argument questioning the stability of our current vacuum emerges from the realms of string theory. Although string theory has yet to yield precise predictions, it strongly suggests that stable vacuum states with positive energy are exceedingly rare. Moreover, string theory hints at the existence of new fields that could shift to different vacuum states far more rapidly than the Higgs, perhaps within the next trillion or even 100 billion years. Now for the bad news. If our universe resides in a metastable vacuum, susceptible to change due to quantum mechanical fluctuations, our concerns extend beyond a mere big freeze. Quantum tunneling to a more stable vacuum state could profoundly transform the very fabric of our universe. This wouldn't just alter how space expands, but could radically change the properties of fundamental particles and the laws of physics that govern everything. For instance, if the Higgs field transitions to a new vacuum, basic particles like protons and electrons could have entirely new masses, rendering atoms and molecules as we know them unrecognizable. Alternatively, if we transition into a new vacuum as predicted by string theory, we might encounter entirely new particles never before observed. Earth would almost certainly be doomed. As for the universe, its ultimate fate would hinge on the properties of the new vacuum state we find ourselves in. Now, let's shift our focus to the other side of our flowchart, where dark energy is derived from new fields rather than the vacuum. These fields can evolve over time, shaping the future of our universe. Unlike vacuum states, which maintain constant energy until a sudden transition, fields can gradually gain or lose energy. Imagine a ball rolling across a rough patch of grass, where the friction causes it to slow down. This is how most fields are expected to behave, with their energy decreasing over time. However, physicists have proposed the existence of exotic fields known as phantom dark energy. These fields defy the usual friction and actually gain energy over time. Such fields could wreak havoc on the universe. As their energy continually grows, they would eventually surpass the energy of all other forms of matter, even within galaxies. In this scenario, the relentless increase in phantom dark energy would lead to a catastrophic event known as the Big Rip. This catastrophic outcome entails the universe being torn apart at every scale, from galaxies to solar systems, planets, and even atoms. Everything would be ripped to shreds by the ever-growing repulsive force of phantom dark energy. On the other hand, if the energy of these new fields decreases over time, the universe might gradually slow its expansion, potentially leading to a big crunch, where the universe collapses back into a singularity. The fate of the universe depends on the delicate balance of these mysterious fields. In conclusion, while the exact nature of dark energy remains one of the greatest mysteries of our time, exploring these theories helps us inch closer to understanding the ultimate fate of the cosmos. Whether we face a big freeze, a big rip, or a big crunch, the universe's destiny continues to be a captivating enigma, inviting us to unravel its secrets. In the case of phantom dark energy, the entire Milky Way would face an increase in energy that heats up the universe, reversing the cooling trend of the past 14 billion years. This scenario leads to an accelerating expansion of space so rapid that any region of space could grow to infinite volume in a finite time, possibly just a few billion years from now. As space expands at this unprecedented rate, calling for help becomes futile. The cosmic event horizon would shrink to the size of our galaxy, then our planet, and eventually down to the size of our home, and finally, us. During this process, the repulsive gravitational effects of phantom dark energy would become overwhelming, tearing apart molecules, atoms, and nuclei into their fundamental components. This catastrophic event culminates in a new type of singularity called the Big Rip, where the universe becomes infinitely big and hot, as opposed to the infinitely small and hot singularity of the Big Bang. Despite this grim possibility, there's hope that phantom dark energy exists only in theoretical models, and that the actual dark energy in our universe behaves more peacefully, losing energy over time. So, if dark energy gradually diminishes, what could be the universe's ultimate fate? If dark energy decreases, the universe might slow its expansion, potentially leading to a big crunch where it collapses back into a singularity. Alternatively, the universe might reach a stable state, neither expanding nor contracting significantly. The destiny of the cosmos remains one of the most captivating mysteries, prompting us to continue exploring and seeking answers. As we unravel the secrets of dark energy, we edge closer to understanding our universe's fate. Whether we face a big freeze, a big rip, or a big crunch, the journey of discovery continues to be an exhilarating quest filled with awe and wonder. Here's where our flowchart starts to get a bit messy, as there are countless ways a dark energy field can evolve over time. To predict the universe's fate in this scenario, we need to answer two key questions. First, can the dark energy field have negative potential energy? Second, does the field's energy change slowly or quickly? If the field's energy is always positive and it decreases very slowly, it would closely resemble vacuum energy. In this case, we'd be heading toward another big freeze. Conversely, if the field's energy drains quickly, the universe would soon run out of dark energy altogether. The expansion would halt, and the future would then hinge on the universe's spatial curvature or its shape. In a flat or open universe, the cosmos would eventually drift toward heat death. But without a cosmic event horizon, we could communicate with galaxies as far as we can see, making this the most peaceful of all possible futures. However, in a closed universe, the expansion would eventually stop and reverse, leading to a collapse back in on itself, a scenario known as the Big Crunch, which is decidedly less peaceful. These potential outcomes highlight the complex and dynamic nature of dark energy. As we continue to study and understand these fields, we inch closer to uncovering the ultimate destiny of our universe. Whether we face a big freeze, a big crunch, or something else entirely, the quest to understand our cosmic fate is an endlessly fascinating journey. Having a closed universe is just one of two paths that can lead to a big crunch. The other path involves the dark energy field reaching a negative potential energy. When this happens, it's only a matter of time before the universe stops expanding and starts contracting. During this contraction phase, gravity turns into a force that accelerates the field's evolution, adding energy instead of depleting it. If the field gains energy slowly, the universe will have ample time to recollapse fully, resulting in a dramatic big crunch. However, if the field gains energy rapidly, the universe could reach temperatures reminiscent of the Big Bang before the Milky Way even collides with Andromeda. In this scenario, the space contraction would be so subtle that it would hardly be noticeable until Earth is incinerated. So, what happens next? Models suggest that if the universe heats up to extremely high temperatures while contracting, it could trigger a new phase of expansion, allowing it to cool down once more. This transition is known as the Big Bounce. Interestingly, the universe could experience a big bounce after a big crunch as well. These scenarios introduce the concept of a cyclic universe, distinct from Penrose's idea of conformal cyclic cosmology. The notion of a universe that continually cycles through phases of expansion and contraction offers a captivating glimpse into a potential cosmic rebirth. As we explore these theories, we gain a deeper understanding of the intricate dance of cosmic forces that shape our universe's destiny. Whether we face a big crunch, a big bounce, or another cycle entirely, the mysteries of the universe continue to inspire awe and wonder. In previous videos, we've discussed Penrose's theory of an infinite sequence of expansion, cooling, contraction, and reheating. In this cyclic universe, even our own Big Bang 14 billion years ago could have been a big bounce, linking our universe to countless cycles that came before. This concludes our master flowchart of all the different ways the universe could end. It could freeze to death, be ripped to shreds, be crushed to oblivion, or heat up so rapidly that it bounces into a new life cycle. While we don't have certainty yet, narrowing it down to these four possibilities is an enormous achievement in science. Our journey begins with the concept of cosmic expansion. The universe has been expanding since the Big Bang, but what's fascinating is how this expansion is accelerating. We'll explore how dark energy, a mysterious force, is driving this acceleration and what it could mean for the future of the cosmos. Could the universe expand forever, or is there a limit? One of the leading theories about the end of the universe is the Big Freeze. This scenario suggests that as the universe expands, it will gradually cool as galaxies drift apart and stars burn out. We'll discuss the timeline for this chilling end and the scientific principles behind thermal equilibrium in an ever-expanding cosmos. In contrast to a slow and icy fate, the Big Rip presents a more dramatic end. Here, the universe's expansion could tear apart everything from galaxies to atoms. We'll break down how the increasing force of dark energy might lead to such a catastrophic unraveling, exploring the physics behind the ultimate limits of matter and energy. The concept of heat death involves the universe reaching a state of no thermodynamic free energy to sustain motion or life. It's the epitome of entropy, where everything reaches a uniform temperature. We'll examine how the laws of thermodynamics guide this theory and what it means for the future of energy in the universe. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.